Hello, this tutorial is about using the K-Means clustering plugin, which is already available on the Unreal Marketplace. This step-by-step guide will walk you through its usage, from setting up the display to understanding the logic behind it, including the data source, injecting values into the K-Means algorithm, and displaying the results. This easy-to-follow video can help you tackle the most technical questions related to this plugin. So, grab the plugin and let's get started. K-Means clustering is a popular clustering algorithm. It's an unsupervised method used to categorize unlabeled data into groups, or clusters. The K in K-means represents the number of clusters. The algorithm works by iteratively assigning each data point to the nearest cluster based on distance metrics. The process continues until the cluster assignments no longer change, indicating that an optimal clustering solution has been found. First, create an empty level in the content browser and rename it as L_K-Means tutorial. Next, create a material named M_K-Means mat. Open it, and create a vector parameter node. Connect this node to the base color pin and multiply it by a value of 1.5 to the emissive field. Don't forget to change the default color value in the vector parameter node and then click Save. Afterwards, drag out the sphere from the Place Actor tab and locate the static mesh asset. You'll find it inside the engine folder. Copy it into our project folder. If you want to optimize performance, you can enable Nanite. Although I skipped this step in the video, I recommend doing so if you plan to have thousands of this type of mesh in your world. The next step is to create an actor type blueprint and name it BP_K-Means small sphere. Add a static mesh component to it. Select the mesh that we copied earlier and change its color. Finally, adjust the scale value to 0.15. Click Compile and Save to finish this part. Next, duplicate the small sphere and rename it to large. Double-click to open the large one and adjust the scale value to 0.5. Remember to click Compile and Save to apply these changes. Now, create a new actor type blueprint and name it BP_K-Means tutorial. In the class defaults, search for the word input and look for the auto receive input option. Set this option to player 0. The next step is to create some variables. Start by creating a small sphere pool to store all the spawned small sphere actor instances into an array. Duplicate this array and create a large version. Then, create a color list array using the linear color type. This will store the list of colors we use to represent the sphere color, which also corresponds to the clustered group color. Don't forget to click Compile to see the default values in the newly declared variable. Finally, use 3 slots to store different colors in the color list variable. I use red, green, and blue for representation. Feel free to use your own color scheme. Next, add a new variable named points, data source, and select the C3KMC.3D type. You can search for the keyword KMC, which is an abbreviation for the K-Means clustering plugin. This keyword can be used universally in searches, functions, properties, or blueprints. I've implemented this keyword in all plugin-related items. The C3KMC.3D type represents a basic data input for the K-Means algorithm. It includes the following components. Unique identifier, this is the ID of the data. X, Y, Z, these represent the original location of the data point in 3D space. Group ID, this is the value assigned to the data after it has been processed by the K-Means clustering algorithm. It represents the cluster group to which the data point belongs. Remember, the group ID is not assigned until after the data has been processed by the K-means algorithm. In this tutorial, I will create a 3D grid of data points, specifically a 3x3x3 grid. This means there will be 3 floors, each containing 9 points, to represent the data source locations. The distance between each data point is 100 units, resulting in a total of 27 data items. If you prefer to skip this step, you can find the same data in the plugin folder after purchase. All the files used in this tutorial video are included in the plugin package. Next, in the event graph, locate the begin play event. Drag out the points, data source, variable and select get. Then, connect it with a for each loop node. This will allow the program to iterate over each point in the data source when the game begins. Next, drag a line from the array element pin and search for the break node. You can see the same KMC point 3D type here. You can get every data in each point here. Then, search for a node called spawn actor from class and connect it with the for each loop. In the spawn actor node, input the class BP_means, small, sphere. In the spawn transform field, right-click the orange pin and select split struct pin. This will split the orange transform into a yellow vector. Repeat this process to further split the yellow vector into green floats. Connect X, Y and Z green pin. Afterward, add a group comment box to indicate that this node can spawn small spheres. Finally, ensure that the collision handling override is set to always spawn, ignore collisions. This ensures that the sphere actor will always spawn into the world at the original location, regardless of any potential collisions. Next, we'll spawn the large sphere. The large sphere represents the center, which is the center point of a cluster group. Let's get started. First, we need to create a for loop node. Please note that this time, we won't be using the for each node. The number of iterations is determined by the value of k. In the context of k-means clustering, the k value represents the number of clusters or groups that will be displayed in the world as spheres. Set the starting value to 1 and the ending value to 3. Next, drag out the execution pin to create another spawn actor from class node. This time, we'll be injecting the BP_means large sphere into the class property. It's important to ensure that the collision handling override is set to always spawn, ignore collisions. This setting allows the spheres to spawn regardless of any potential collisions. Next, drag out the set actor hidden in game node from the return value blue pin. Make sure to check the hidden Boolean parameter. This action will hide the large group sphere at the start of the game. Now, let's organize the graph again. I forgot to mention earlier that in the large spawn actor node, you should also input an empty transform. Drag out the spawn transform pin and select make transform. This step is crucial to avoid any compile errors. Once you've done that, click on compile and save. Then go back to level editor. In content browser, drag out the BP_k-means tutorial into the world. When you click play in editor, you should see the same result as mine. All the small spheres are spawned, and the large sphere is hidden. Once the scene setup is complete, we need to store the small spawned actors. To do this, access the small sphere pool and use the add node. This action will add all the spheres into the pool. Please remember to repeat this step for the large sphere as well. It's crucial not to forget this step, as it ensures that both the small and large spheres are stored properly. The next step involves spawning the k-means handler. This handler is responsible for all the data calculations and processing using the k-means algorithm. You can think of it as the brain that helps you process k-means. This plugin provides both a 3D and 2D version, and it supports multiple handlers working simultaneously. So, if you need to calculate different k-means, you can create multiple k-means handlers. After creating the handler, it's important to verify that this action was successful. To do this, add a branch node and connect it with the return value pin. Then, drag out the newly spawned k-means handler blue pin and select promote to variable. This action will automatically create a new variable of the related type for you. Now, let's take a moment to organize the graph. You'll be able to see all the nodes directly in the plugin files. I've made sure to maintain the highest quality of documentation for your convenience. Next, let's calculate the main action for k-means. First, we need to create a node called key-q. This allows us to perform the k-means calculation once we press the Q key. Next, drag out the k-means handler variable and select Get. From the k-means handler, drag out the Initialize Main blueprint node. The Initialize Main node allows us to initialize all the prerequisite data in one go, making it both convenient and user-friendly. If you want more control over your flow, you can choose other initialization nodes such as Initialize Points, Initialize Iteration, Initialize K-Value, or Initialize Center's start location. In the point list parameter, input the points, data source, variable. This is where we inject the data source, referred to as points. Then, change the K-value to 3. For safety reasons, connect a branch node after the initialization to ensure all inputs are correct. Afterwards, drag out the k-means handler again and look for a method called run k-means main, multi-thread. This is the main method for calculating k-means. Note that this is a multi-threaded version, which means the entire calculation won't block the game run and won't affect performance. You'll notice that there is a red event pin labeled on finished calculation. But before we proceed, drag out the is ready to run node from the k-means handler to ensure no calculation is currently running. Keep in mind that if a calculation is already running, it cannot accept new tasks. In our experiments, most tasks can be completed within 1 second, even when the data size is 10,000 and the iteration is 100. Use a branch node to connect the flow as shown in the video. So now we finished the calculation part and initialization part. Now, let's turn our attention to the unfinished calculation. Drag out the red pin and look for Create Event. In the Select function field, choose Create a Matching Event. This will automatically create a related event for you and connect the unfinished calculation to this newly added event. This event will be triggered when the k-means calculation is complete. Next, let's examine the result pin. Drag it out and select Break. You'll see that this provides an array of points and an array of cluster center information. Additionally, Centers Single stores the clustered group which contains only 1 point, while Centers Group stores the clustered groups which contain more than 1 point. The member list is a mapping between the group ID and the related points. This allows you to easily identify which points belong to which group. Next, drag out the k-means handler and look for the getPoints method. This will retrieve all the data points. We then need a for each loop node. Input the point return value into the array parameter pin and connect the red event node to this for each loop node. Drag out the array element and choose Break. This will display the point data that is currently being iterated. Next, drag out the small sphere pool variable and select Get a Copy node. Connect the array index pin to the Get Node Index parameter pin to retrieve the corresponding small sphere actor. From the Get Node return value, look for the Get Static Mesh function. This retrieves the static mesh component in the sphere. Next, drag out Set Vector parameter value on materials from the static mesh component and connect it with the For Each Loop execution pin. In the parameter name pin, change the text to color, which we defined in the material at the beginning. Right-click the vector parameter and select Split to expose the XYZ separately. Then, retrieve a color list variable and choose Get a Reference node. Connect the group ID to this getter node. Then break the color return value, and you will see that R, G, B, A are displayed. Now, connect R to X, G to Y, and B to Z. Great! Now that we've set the small sphere display up, it's time to organize the graph. Once you're satisfied with the setup, you can hit play in Editor to see the result of your k-means clustering. That's right. When you press the Q key, the k-means clustering result will be displayed. Each color represents a unique group, making it easy to distinguish between them. One of the key advantages of this plugin is its speed. The calculation is extremely fast, allowing for efficient data analysis. This makes it a powerful tool for understanding complex data sets. Now, let's create the large spheres that represent the clustered groups in the world. The steps are very similar to those for the small spheres. First, get the k-means handler and drag out the getCenters function. Then, use the for each loop, inputting the centers into the array pin. Connect the for each loop with the complete pin from the previous loop that spawned the small spheres. This way, the small spheres are displayed first, followed by the large spheres. Next, drag out the array element and break it. Then, get the large sphere pool variable and choose the getACopy node. This will retrieve the iterating large sphere pool. Drag out the return value from the getter node and look for the setActor hidden in game function. Make sure the new hidden is unchecked. Connect this with the for each loop. The next step is to set the actor location. Make the large sphere change its location based on the center's location. Right-click to break the location vector into x, y, z floats. Finally, repeat the color list action like you did for the small spheres. This will make the large sphere the same color as the related small spheres. Great! Now that we've set everything up, it's time to organize the graph. Once you're satisfied with the setup, you can hit play in Editor to see the result of your k-means clustering. Remember, the beauty of this plugin is that it allows you to visualize complex data in a simple, intuitive way. Enjoy exploring your data. That's right. The small and large spheres in the world represent the points and centers data respectively. This visual representation makes it easier to understand the results of the k-means clustering. For advanced usage, this plugin offers the ability to simulate more data sources by generating random points. To do this, navigate to Begin Play, drag out the points, data source, and set a new value to override its default value. Use the node called Make Random Points, 3D, to generate more data. I've set the number to 1000 and the random range to a distance of 500. Place this node before the start of the small sphere spawn. This will override the data source. In the large sphere, which represents the clustered group, we can use the color list as the number of groups we want to cluster. This is equivalent to a k value. Drag out the color list and look for a length node. The length of colors also represents the k value, which in turn represents the number of large spheres needed to spawn. Connect this with the last index in a for loop node. In the keyQ event, look for the initialize main node and change the k value. Use the color list and length node to replace the k value pin. Now, if you have more color elements in the color list, the k value and group will increase accordingly. But first, let's check the current progress. Afterwards, we can add more custom colors to the color list variable. I have a total of 7 elements, so the k value in my scene would be 7, and 7 large spheres will appear. You'll notice that even with 1000 data points, the calculation is still fast and won't affect the main game's performance. In conclusion, this plugin provides more advanced demos and tutorial files, which you can explore in the plugin folder. If you can't find it, navigate to the Settings button in the Content browser and enable Show Plugin Content. Then, search for Cyrus 365, k-means clustering content. The tutorial files are located in the Intro tutorial folder, where you'll find all the related blueprints or materials. For a more advanced demo, check out the Advanced Demo folder and open the L_KMC_demo level. This is another 3D demo project, but with lots of customized steps in k-means. Unlike our previous project, this one doesn't use the initialize main, but instead uses initialize kValue, initialize points, initialize iteration, and initialize center random location. In addition to the 3D mode, this project also offers a 2D mode for users who prefer a simpler visualization or for datasets that are better suited to a 2D representation. The workflow remains largely the same, the only difference is that the structure changes from 3D to 2D, and you would use the 2D handler instead of the 3D one. This flexibility allows you to choose the mode that best fits your data and your visualization needs. This advanced project also includes UI-related content. So, you can see how the UI links to the functionality. Everything is well documented with comment boxes to help you easily understand the code and its purpose. Feel free to explore and test it out. This hands-on experience will give you a deeper understanding of K-means clustering. In conclusion, the K-means clustering plugin for Unreal Engine is a powerful, user-friendly tool that brings the power of clustering data to your fingertips. With its intuitive interface, advanced features, and efficient performance, it's never been easier to implement K-means clustering in your projects. The K-means clustering plugin will be featured in the Unreal Engine Marketplace Showcase rotation from January 23 to February 6, 2024. What's even better is that during this period, there will be a whopping 50% discount on the plugin. This is a golden opportunity to get your hands on this powerful and user-friendly tool at half the price. Purchase the K-means clustering plugin and start exploring the world of data like never before. Happy clustering!